if you simplify too much, then you will lose the essence of it. And also, in addition, if you're not sure about what is your goal, and this is a thinking we need to get rid of it when we compare different technologies. So that makes sense. If I have a lithium-ion battery and I have another lithium-ion battery, they have the same power characteristics. So it's completely fine to compare the kilowatt hours performance. But if you're really like working with flow batteries where the ratio between power and storage is quite different, like 1 to 4, 1 to 8, maybe even 1 to 60. So you can discharge at the highest power, maybe for a whole day even, yeah. So then this whole calculations of the kilowatt hours don't work anymore because you need to think about the levelized cost of storage. So how much can I earn with the battery? We started like from university in technology development, and it's now, I think since the first idea I had, like that was 2014. Proof of concept we had maybe 2018 in the lab. So we patented and published in 2020. So it was 6 years from the first idea so that it's working. And then we found a company which took another 2 years to get all your business plan thinking done. It's such a complex project, which requires a lot of multidisciplinary thinking. And our team is luckily very good in that.
Hey, I'm Al, and this is the Paglalayag podcast. I'm using this podcast to showcase what's going on around me in the hardware and clean tech sectors dito sa Philippines. With guests from across the startup, research, investment, and enabler ecosystems, Paglalayag focuses on the stories and inspirations that motivate us to start up in hardware and press on down this arduous path of steering our economy away from the looming climate catastrophe that makes itself increasingly felt in our lives each passing year. I hope you'll find this cast of characters as impressive and inspiring as I do. Also, if you've been listening to these podcasts and want to let me know what you think, there's a survey form available at paglalayag.net-podcast. You can also reach out by email at al@paglalayag.net. I'd love to hear from you. Sige, tuloy-tuloy lang. Let's jump in.
All right. So welcome everybody to Paglalayag. I'm Al, and today I'm joined by Stefan Spirk. Stefan is CEO of Ecolyte, and Ecolyte is building a next generation flow battery using water and vanillin. Vanillin being the active substance that gives vanilla its smell, but also comes from a number of other biological processes and materials, which we'll let Stefan explain a little later. So thank you very much for joining me, Stefan, from Portugal, from sunny Portugal. I can see it's very sunny over there.
Hey, Al, nice to be there.
Yeah, cheers. So we
Cheers.
met at Science Park. You were part of an Austrian delegation to visit Hong Kong to show off the different kinds of technologies that were under development in Austria. And yeah, we kind of hit it off from there, being doing our supercapacitor work, which is sort of like high power, low energy. On the opposite end of the spectrum is maybe the flow batteries, which are a little bit more of a big energy play, but not necessarily the same speed or power. So yeah, that's how we met and hit it off. So why don't you get started by just telling us a little bit about where Ecolyte's at now?
Yeah, so basically, we have been founded in 2022 in Graz, in the south of Austria. And yeah, we have now 10 employees after a little bit more than 2 years of operation. It was very difficult to get the funding done because nobody believes you, that you can build such a thing, very capital intense, very work intense, high risk. And yeah, so luckily we got a very good traction in public funding, got really big projects going on, and can finance now also the prototyping. In addition, we have an investor who's like part of or like an energy company, small energy company close to our headquarters. And with this investor, we're building now our first prototype battery, so which will be having like a 10 kW power rating and maybe a 20 kilowatt hours in storage. Not too big, but still for flow battery research, quite an achievement actually. That's where we are right now. So this is what we are doing the next few weeks. This will go in operation. Yeah.
Yeah, and I mean, when you say say prototype in the context of flow battery, You're talking about something much more substantial than what many startups would be talking about when it comes to prototyping. Like in the really extreme case of like just software, you can hack together a prototype with some coding in a number of hours. It's not like that with flow batteries, is it? What is the last prototype you made, and what is your next prototype going to be?
I think the last basically a stack with 8 cells. And now what we're doing is big stacks. Like we will have 4 of those stacks, 4 to 6. So in the end, 6 in the beginning, 4. And we will assemble those stacks in a container where we already can scale further. So it's just like having small building blocks where you can basically go larger and larger all the time. And this is not what's typically startups do in the software range, because they are really like, as you said, they have like software or things like this. So it's very different. It's very small cells. Also, like when you're talking about hardware, it's typically very small things. This is very big, so it's a real full ship container.
Your vanillin comes from the forestry industry, right? Like, can you explain a little bit about how you're getting vanillin? How does it smell? Is it smell as good as vanilla would, or yeah? Like, how do you go through that whole part of the process for your startup?
I can just tell you a story. You know, when we ordered the first 40 kilograms of vanillin, it came when nobody was there in the company, so it ended up in my office, and it was there the whole weekend. And I went to my office and thought, oh, it's a nice smell. But after 2 hours, I got a headache, you know, because it's too much. It's like with perfume, you know, if it's too much, it's not good anymore. So in small doses, vanillin smells very nice, but in high doses, it's also not so nice. Just to be honest. However, what we are doing is we are like modifying the vanillin, chemically modifying it in order to use it for the energy storage purposes. So we are using very simple chemistry, very sustainable chemistry, no organic solvents, no toxic substances. And in this way, we can really like get to these energy storage materials.
Cool. So how do you describe like, because obviously you need to make a business out of this. Like how do you think about scaling? Like you're doing stuff at the bench level and trying to demonstrate certain technical capabilities, but then also having an eye on how you would actually make a commercial application that does find its way eventually to profitability. How do you think about the scaling of the economics and the profitability side alongside the technical deliverables that you have to make sure you deliver on as well?
It really goes hand in hand. So there is no how to say it. It's not separated topics. So when my coworkers come or my employees come and say, I have this idea to improve, then I ask, okay, can you do it in the kilogram scale? Can you do it in the ton scale? I mean, not like at the moment, you know, but in general, is it possible? There are things you cannot do in large scale, and then forget about it. Just not do it, because things get cheaper when you do it in large scale. So you always get into the economy of scales at some point. Is the one thing, and the other thing is you need to also think about minimum waste. You know, so you are not you must not have any waste materials in your process, because if you have a large amount of materials, this would just kill you. So you need to have quantitative yields when you do chemical synthesis. Also, when you are working like with extraction or whatsoever, you need to be sure that you don't create waste, because on large scale this will kill you. This is always part of the thinking from both technology and economic side. Very important thing in my opinion.
And when you think about how things are today, and if you did just like sort of hit the breakthrough you're looking for from a technology and sort of like having everything well balanced from the economic side, where do you see the biggest challenge in like rollout? Like where do you think the bottleneck would be?
It's a very difficult question, Alan. But
I
I know
know.
that you will ask this difficult question.
I,
I
I
mean, the thing is always like this. I would say the world is looking for battery solutions that are not flammable, that use like renewable materials, and however, they also need to be affordable, right? So if the batteries are too expensive, they will not penetrate the market. And from my point of view, the biggest barrier at the moment is a regulatory side. So it takes quite long to build big batteries still, you know. So and in Austria, for instance, we still have some laws that are treating a battery like a power plant. So that means you have to pay money to take energy into the grid again. So that doesn't make really a good business, doesn't, or makes it more difficult to get a business case out of it, because these fees are quite high, and maybe the electricity price is cheaper than the fee. So you cannot earn money with this. So that's one thing, like by directly trading electricity. So this is the one thing. So you would need to have maybe a more uniform legislation all over the European Union. That's the one thing. Maybe desirable like globally, but I'm realistic, so I can just think about a European perspective right now. So this is the one thing, and the second thing is that I think is a barrier is that people tend to compare the systems just by the price per store kilowatt hour. And this is a thinking we need to get rid of it when we compare different technologies. So that makes sense if I have a lithium-ion battery and have another lithium-ion battery, they have the same power characteristics. So it's completely fine to compare the kilowatt hours performance. But if you're really like working with flow batteries where the ratio between power and storage is quite different, like 1:4, 1:8, maybe even 1:60. So you can discharge at the highest power maybe for a whole day even, yeah. So then this whole calculations of the kilowatt hours don't work anymore, because you need to think about the levelized cost of storage. So how much can I earn with the battery, and what are the real actual costs over its lifetime? So that means capital costs, running costs, also costs for deinstallation or recycling or disposal of materials. So this is, I think, one of the things we really need to tackle in some point, yeah. So like it's a thinking in the people's heads, and so to really see what is the real cost of the battery, basically. I mean, just an example, if you use a lithium-ion battery, after, let's say, a couple of years, 7 years, you will lose a significant amount of capacity, right? So 15, maybe 20, depends on how the battery was used, what's the history of it, maybe even more. And in addition, you don't, I think you cannot use it even a second life, I think, reliably, because the danger of fires is quite high with those batteries. So you would need for like lifetime of 20 years, if you consider that realistic for a flow battery, then you would need 3 of such batteries, right? So it would triple the costs. You get my point? So I think that's the thing you should think about. So it's not so easy. And the second thing is really how to use the battery. How many cycles do you need per day? What's the power that you need? Yeah. So which stationary energy storage application you want to have. So I mean, flow batteries, they're just big and they're heavy, but they are ideal for particular stationary storage application. You talked about supercaps. They are very nice for like frequent system, very fast response, millisecond response, very high power in short time. And the flow batteries, they come into play maybe after 20 seconds or something like this. They can do the same thing, yeah. So on a different scale. So when the capacitors are gone, and the flow batteries can step in. So this also shows how these applications are kind of like interwoven and interconnected with each other.
20 seconds. So how does that work? You like turn a valve, you like open a valve, start the flow running, and within 20 seconds you've got your voltage or you got your power, or what?
Yeah, exactly. It takes like that long that you have a stable voltage, I would say, for a larger system. So that's typically what you find also in literature. So this is like 20, 30 seconds for this, frequency stabilization. I mean, in theory, it should be a bit faster, but you just need to think about if you have large volume flows, it takes a few seconds until you have it, and then you cannot go from the very first second and take the full power out of it. So it needs to be just stable running.
Right. So I mean, like that's plenty if you're talking about like I mean, in supercapacitors, we talk about peak shaving, like on the order of like seconds or less than seconds, milliseconds, like you said, filtering. But if you were doing peak shaving, like the duck curve, like they talked about in California, I mean, it's every grid really, where like the power is going up in the morning, and then the power it goes down during the middle of the day and goes up in the evening again when everyone gets home to watch the news or whatever. You're easily in the right time frame, or you're easily doing that with 20 seconds.
I would say so. I mean, we have also now a research project going on where we have access to real-time data in the Austrian power grid, where we have a lithium-ion battery in there, and we clearly see how this battery is charged and discharged. And I think that's also when you develop such a technology, you think about, okay, I can charge this charge, blah, blah, blah. And this is your idealistic thinking. But when you see the battery in real life, and how it's charged and discharged, it's sometimes not very intuitive when you look at it in first instance. You would just expect you only charge when energy is very cheap. But that's actually not true because the algorithms know that energy will get even more expensive and you still charge a battery when it's quite expensive already, but you can still make a profit out of it. Yeah, so because you can provide the energy for more money a bit later, or you can save energy actually, or save the money for the energy. So that's also like the bill management application. So where you just buy it cheaper, so to save the costs later. So this is, I think, also some of the applications are targeting this area, this field. Yeah, just a side note.
Yeah, well, that's great because Philippines really doesn't have much in the way of time of day pricing. So they're not there's that like that. That's not really part of the conversation when it comes to renewable energy or anything like that.
Okay.
What so is that kind of energy arbitrage, like trading sort of strategy, part of your business model?
Yeah, it's also. I think these are two. It's the same. Let's say the same thing you do with the battery with two different applications. If you do energy arbitrage, it's like you're just selling the energy directly, right? So that's what you're doing. So you buy cheap, you sell more expensive. And for the bill management, you just save the energy for a later point to use it yourself. To
Sure.
save costs in your company. So this or in your business or whatsoever, or I don't know for what purpose, but this is the second application. I think maybe another one that is relevant for the stationary system is also TNT deferral. Yeah, so that you are trying to lower the peak power that you need in your industrial complex, in your park, I don't know, business parks and whatsoever. So, for instance, in Austria and Europe, it's like this, that when let's say you need a maximum power rating of 1 megawatt, for instance, you have to pay a certain amount of money, to upgrade this to 1.1 megawatt. It's quite expensive to do that. But if you have a battery, you can just leverage, this scale up for a while, because you can just use. If you really need more than one, then you have the battery to go in and jump in, like these few times a year or these few times in a month, or maybe also more often to really save these costs. So that's also one of the applications we target basically with our battery systems.
Sort of like a bit of a modularity of capacity increment, like adding incremental capacity in a more
No
modular
power.
way.
Power. It's about
Right.
power, actually.
Okay.
So to have more power, it's also, I think also lithium-ion batteries can be used for that, just to extend the power available in a certain environment. So as I said, you have maybe you have the wires, the grid is giving you 1 megawatt, but at some point you need 1.1 megawatt. So what are
Mm.
you doing? You can ask to build a larger like wires or more grid and things like this, quite expensive. Or you can say, okay, I use for this excess, I use a battery that provides then this energy over the time I need it for. Yeah.
And when you're thinking about like how you're charting your own company and strategy, are you looking more because there are commercial flow batteries in the market, but when you talked about this, you mentioned lithium ion. Would you say that you are following the cues of the flow batteries more or like, I mean, obviously everybody knows about lithium ion batteries and that's probably why you did it. Do you feel like the flow batteries are sort of like have their own niche that at this point or still kind of finding their niche?
I mean, they are a niche technology in a way, because lithium-ion batteries have become so cheap because of the mobility, economy of scale. So that's the one issue, and it's out of doubt that probably we have reached already more or less the bottom. I mean, they will get a bit more cheaper, but I don't see that this can go much further down. But for the flow batteries, like particular vanadium, you have the problem that the raw material costs are very high. So it's a technology that's working. So raw material costs are high, and you have a very aggressive medium like sulfuric acid, and this makes all the other materials that you need to build up the battery quite expensive because they need high chemical resistance. So these are the shortcomings of the vanadium. On the other hand side, it gives you high cell voltage. It has been researched a lot, so there's a lot of knowledge available in the domain, also about business cases. And this we target to have the same benchmarks, of course, right? I mean, we cannot like just say we are like cheaper, but we cannot like bring the performance of a vanadium battery. So I think we should be able to do the same. We will have, of course, issues with cell voltage. We will not be as high as vanadium, but we are optimistic to reach the 1 volt, like 0.9 volt, which we need for a business case quite soon. I think this is one of our targets that we have. And then it's just an economy of scale to get all this technology developments cheaper.
Do you have a large voltage drop, like relative to, like, say you're like per watt? Like I don't know if I'm speaking to the right metric here, but like say you were to pull a watt out of a certain like amp hour, like let's say an amp hour cell, and you're gonna pull a watt out of it at whatever. Would you have a relatively large voltage drop compared to lithium ion, or
It's very how to say I mean there's a voltage drop in flow batteries, of course, because there's a lot of phenomena taking place, and also in our batteries we see, and I think at some point you cannot avoid it. Like the absolute value will always be approximately the same, but the higher the cell voltage is in percentage, the less important it gets, right? So because the voltage drop comes from on one hand like the ohmic contribution, which is basically the resistance of your system, so they can be optimized to a certain point, and then you have diffusion and activation processes that are like on the electrode surfaces. So this can also be optimized, but at some point you end up in a minimum value, which is maybe 0.1, 0.2 watts, you know, and so this also reduces the efficiency of the battery as a whole, basically. So this is also one thing you should consider. That's also better for lithium-ion batteries. You have very high efficiency, 95%, 90%, depending what you calculated for flow batteries. You have 75%, maybe, or 80%. So these are the two. There's a big difference. I mean, for flow batteries, you create a lot of heat. I mean, that's also like what you do, and particularly for vanadium. And this heat is, particularly for vanadium batteries, a problem because the vanadium is precipitating from solution at about 40 degrees, a bit lower than that. And then you really need to spend a lot of energy for cooling. So that depends then where this battery is located, how the economics is. For our organic batteries, we see that the electrochemistry gets better because that's according to the Nernst equation. Electrochemical properties get typically better when you heat systems up, right? So because temperature is our friend here. So when you go up, when you go down, we know it from electric cars, you know, then the capacity goes down. Like that's also how it is. So because yeah, it's part of physics. We cannot trick physics.
is the heat from the charging or the discharging or both?
I think it comes from both things. It's about resistances that you have on the electrode interfaces, and I mean there a carbon mesh in there like a felt, and there you create some hotspots. And there, of course, I mean you have thin wires, micrometer thin wires, and of course you have a lot of energy in there, so it will get a bit warm at some point. Just normal.
So if you had a little while ago, you mentioned that like some of the classical metrics that people talk about with batteries are maybe not the best way to look at flow batteries. Do you think that there's, and then when you gave an example with us, you talked about the supercapacitors having a very short time spike compared to the 20-second ramp up. Like, is that a good framing for the metric, or is there another metric that you think would really be like the sweet spot metric for flow batteries?
I think
the technology.
I think for the flow batteries in general, that's not specific to our technology. It's really about from 4 hours onwards discharge time. So these are the systems where you can really benefit from it. So 4, maybe better, even 8 hours discharge time, charge discharge time. So this is basically what the lithium-ion batteries cannot deliver at such a cost because, you know, I mean, some lithium-ion batteries you can have a 1-to-2 power to capacity ratio. Typically it's 1-to-1, so it's very difficult. So you need a lot of capacity in order to achieve the power, right? So that's the other way around. So that means it gets more expensive then also with the stationary storage for lithium. It's not as cheap as it is for the cars, for instance. Also safety precautions you need then. But anyhow, the sweet spot is definitely at long discharge and charging times. Also
And
from an economic point of view. I mean, there are these calculations on levelized cost of storage, like not only our own calculations, but also those from the Lazar study, where you compare different types of energy systems, supercapacitor lithium-ion batteries, zinc batteries, vanadium flow batteries, and then you end up like in these sweet spots.
like, what would you say? I mean, if we go back to the modularity thing, do you see a sweet spot size for the vanillin system right now, or are you still like
Yeah,
kind of?
we have simulated this already with some with another startup that is working on like algorithms in predicting the performance of a battery. So they are basically predicting the energy market. So they know basically how much will the energy cost tomorrow, you know. So and then they give you an algorithm how to deal with it. Yeah. So or
Hmm.
you is now an energy company, and we were like giving our yeah how to say our parameters, performance parameters to them, and then they were using the German grids, so the real electricity, the real time electricity data from Germany in 2022, and they found out that our sweet spot is basically a 1 megawatt, 4 megawatt hours battery. So with this one, we can make the best profit out of the investment. So if you get larger, then it goes a bit down because you cannot use the full capacity probably at the same time and the full power rating. And if you go smaller, then you don't have enough scale to participate in different types of activities in the market. So you need very often 1 megawatt. You need to go for like auctions that you win for grid stabilization and things like this. So that's a part of the game here in Europe.
How big of a facility or like a reactor do you think that would be?
You mean the battery itself?
Yeah.
That's several containers, I would say. So I would say it's probably, oh, it depends how efficient we can pack the containers in there, but it will be definitely 4 to 8 containers, for sure, big containers, just with the stacks, and then you have the tanks in
So
addition.
like
So
half a football field maybe.
half a football field? No, I don't think so. I don't think so because you will put maybe the containers on top of each other and the tanks maybe on below. So it will be still very compact. It will be maybe a small house. Maybe you can think like this, yeah,
All right.
like the size of a small one family house or something like this.
Okay.
This is what I more see because these containers they have like I don't know they are 3 meters wide and maybe 8 meters long or 12 meters long. So it's not super, no, 8 meters actually. So it's not super big. You need a
Right.
couple of those. So
But you would the cells be sort of like spread out, or would they all be kind of together in a single structure?
they would be in a single structure if you have it like this. I mean, now the plan is like this when you're thinking about I mean, now we are building this 10 kilowatt battery, right? And the idea is to really use this as a starting point to grow it larger and larger once we see it's really like working. And our strategy is really to go with our investor this step, right? Because I mean, you know me now, Alan. We've had a very good time in Hong Kong. I really enjoyed a lot. You showed me even the kung fu, so that was really nice. But I mean, when you buy a battery from me and you want to have a 1 megawatt, 4 megawatt hour system, and then you will just ask me, Stefan, how many of those batteries have you built? And then I say, Alan, I'm very sorry, but you're my alpha tester. So you're the first one who is trying that. But it's very expensive. I get the point. I would act the same. And what we're doing is our strategy is that we build the big battery, the first big battery together with our investor, like at the facility where there is the energy created. And then if you come then there and say, okay, Alan, you see, this is our battery. We know it's working quite nicely for 3 years. Then you have blah, 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 a problem. We will fix that for you, of course. Yeah. And then we have 95% capacity after 10 years. Is that a problem for you? No, that's a different way of communicating to customer, right? Because you need to give some kind of trust that the technology works. And for this, you need a demonstration object, a bigger one. So the step we do right now is to demonstrate that the technology works in a real environment. And the next step would be then to really like scale up quite rapidly to
Right.
larger power ratings. It's more about the power than the capacity. Capacity is the easy thing, but the power rating is really the thing that is important for us.
Mm. And like what the voltage on the cell is, how much did you say it was again?
No, I think for this prototype, it's like technology that is really like it's close to 0.7 volts. So it's not like a commercial thing, so the target is 1 volt. And we just choose this system because it will be close to the things that we will be using in the battery, like chemistry wise, but just to have a prototype in place. So this is it's a very important thing to really have also the other components ready. And when we then have a better chemistry, it's you can think about this. You just change the liquid, and you need less of those stacks in order to get the power. So, or on the other way around, if you use another liquid, you have higher power immediately. So it's also like, and we're designing our system like this that it can also go for this higher powering if you have already considered that in our planning. So technology jump. So it's very flexible. This very first prototype.
Sure. But if you were to go to like 200 mains, like 200-volt mains, you see yourself going actually 200 volts worth of cells, or would you be doing power electronics and something at like a lower voltage point, you think?
It depends on the application. I mean, if you're thinking about industrial grids, they very often like we have an industrial partner, and this partner operates the grids like at 600 volts. So I think that's not the voltage thing is not so problematic for us in my opinion at this point. You need to work like just with DC, AC, like inverters or whatsoever. I don't see this as a problem. I know what your concern is. And of course, we have considered also parallelization, but at the moment, it's not like the thing we are really like, how to
Spreading over.
say, it's not our main concern at the moment. Let's call it like this.
Sure, sure. Okay. Well, I mean, it sounds like a fun space to be in, but I mean, challenging because it's so niche. And of course, like you said, batteries, like everyone knows lithium. So if you're outside of that, then there's a lot of explanation and market education required to even get to the point where you're having that conversation about trust.
Exactly, and I mean, what we're also doing is we're also talking to our competitors, like with vanadium. We have developed now membrane technology, and probably we can use that also for vanadium batteries. And I don't see also the vanadium people as a threat or as a competitor. I think the market is so big. We will never be able to build so many flow batteries for the whole market. It's not simply not possible. So there will be some technologies will be there, and I think I'm pretty sure that there is a lot of space for technologies in flow batteries and in energy storage in general. It's so
Well, you'd
versatile.
probably make a lot of pulp mill. I don't know if they specifically comes from pulp mills, but you'd probably make a lot of groups like that pretty encouraged, feeling pretty good if you could tell them that you had a battery grade application for it. Because I know like when it comes to like nickel and manganese, like they've got what they put into the steel at a certain price per pound, but when it comes to what they need for the batteries like that commands a much higher price, and I'm sure it's the same for vanillin.
Yeah, exactly. When you use it for food grade, I mean that's more expensive than when you use it like for technical purposes. I mean, what we are working with pulp and paper industry on is to really get a new process done. Where we can get the vanillin production even much cheaper than what is possible now. So, and we expect that we can maybe reduce the price by a factor of 4 to 5. Compared to what is now on the market. I think that's like the perspective on it. It's not only about what is possible now. You also need to see what is possible in the future. And I think if we can get this factor of 4 to 5, it will be getting extremely cheap in order to make the batteries.
Cool. Yeah, sounds like a nice. Just to your comment about like not found all over the place. So like you said, you're not going to be building those kinds of batteries all over the place necessarily. But if you could start to be able to build batteries in areas that like have local forestry production, which is a lot of places, then that would become quite interesting for a lot of people, I think.
I think so. I mean, when you say all over the place, it's just like with the first batteries like this. But as soon as we have demonstrated this, we can also think about maybe for business parks and things like this that you can use it. Industrial complexes is an area, also hospitals, military applications, chemical parks and things like this. I think there we see the thing, but we are aware that we need a large scale system in order to justify the investment costs. Otherwise, it won't be a business case in the next 5 years, I would say.
Yeah. Yeah, and then on the other hand, sometimes these investment cycles come when like world events bring people starting to think about energy a lot more, and you never know when those are going to come along. But sometimes like that sort of thing does move whole technologies and industries forward a whole lot in unexpected ways. So
Yeah, exactly. You're completely right. And I mean, these cycles, if you're too early with the technology, is also bad, you know. So then
yeah,
it will be
especially if you're the one
forgotten.
that's putting all the time and effort and out of pocket expenses into it. That that's
Exactly.
not a fun road to be on for that time.
Mm.
Sorry, did you have further thoughts? Did you want to finish that or
I think that's it basically. Yeah. I mean,
okay?
the maybe to summarize, it's I mean, we started like from university in technology development, and it's now I think since the first idea I had, like that was 2014. Proof of concept we had maybe 2018 in the lab, so we patented and published in 2020. So it was 6 years from the first idea so that it's working, and then we found a company which took another 2 years to get all your business plan thinking done. It's such a complex project which requires a lot of multidisciplinary thinking, and our team is luckily very good in that. And yeah, but it's still very hard, you know, because you need to set up the financing, you need to pay your bills, you need to get the right employees, and also find the right partners. But yeah, so far we were quite successful in that.
Cool. Yeah. Congratulations. With Paglalayag, we like to say tule long, which is like keep going. Just keep at her and all the best on that. I'm going to get into the quotes now.
Oh
So
yeah, great, great.
yeah, so I pulled up a couple from Austria, one scientist and one artist. So the first one being Wolfgang Pauli, a famous quantum physicist. And what he said is that if speculative ideas cannot be tested, they're not science. They don't even rise to the level of being wrong. And then, on the other hand, Joseph Haydn, the famous composer, said that young people can learn from my example that something can come from nothing. What I have
I
become
like
is a result of my hard efforts. I posted them into the chat.
I like the second one. I like them a lot. So I like both of them a lot. I like them both. Yeah, I think the first one I even know. Yeah. So do I need to choose now, or how is it?
Yeah, just whatever you got to say about them. You don't need to choose per se. It's I
No,
try to
but
just like contrasting ideas, sort of.
mm, yeah, I guess the second one from Joseph Haydn is it just shows that he's just saying that you don't need talent to become something, right? It's just a result of hard work, which is of course a little bit ironic. I think it's not meant completely seriously. It just should indicate that even if you have talent, you need to work, you know, hard to become something. And I think the first one is also very how to say reflects a bit the thinking of a physicist, hardcore physicist, from the, yeah, when was it there? 30s or something, or 20s to 30s. Just saying that you can only prove something wrong if it's like concrete, right? Of course, if we're talking just blah blah, then you can never say yes or no about it. So I think that's what we very often do, right? Also here in this chat. Like because you want to get the public opinion or the public involved, and if you go too deep into the science aspects, I think nobody would understand anymore. Or even worse, if people try to get like this mediocre feeling of science, you know, so then things can really go wrong, and we see this with a lot of like developments in the world, right? So where like this fake news or whatsoever, that's also like what you have about science, where I've just think about climate change or whatsoever, you know, that comes when people are trying to develop their own reality because it's not concrete at all. So maybe you can also interpret it like that. That's maybe critics and people are making things too simple, you know. Maybe that's the right thing to say,
Nice.
right? If you simplify too much, then you will lose the essence of it. And also, in addition, if you're not sure about what is your goal, then also maybe it's not right way to do.
Uh,
What's your
and how can people get in touch with you? What's a good way to get in touch with Ecolyte?
I think the best thing is just text me via LinkedIn. I think that's a good way, or they can also like check the webpage www.ecolyte.at, or they can also like follow us like on the Vanilla Flow page in the LinkedIn. So we have a page there on news. So there's also a webpage www.vanillaflow.eu where we are working a lot with artificial intelligence to develop the technology further. So there's a lot of things going on there at the moment.
Wicked. So yeah, that's it for us. Looking forward to when you get one of these rocking and rolling in the Philippines.
Let's see. Let's see. I think you just need to invite me, then I would visit you, so then we can see how long it will take. So I'm happy to come over. So small Asia to also hopefully get some more training from you.
Yeah. The check's in the mail. Don't worry, it'll be there in like
Oh,
a day.
yeah, perfect, perfect,
Cool.
perfect.
All right. Well, yeah, Tule long. And thanks a lot for joining, and we'll sign out from here. Cheers.
Okay, okay. Bye bye. See you.